Extreme values and saddle points. Continuous functions of two variables assume extreme values on closed, bounded domains. We see in this section that we can narrow the search for these extreme values by examining the functions. First, partial derivatives. A function of two variables can assume extreme values only at domain boundary points or at interior domain points where both first partial derivatives are zero or where one or both of the first partial derivatives fails to exist. However, the vanishing of derivatives at an interior point, AB does not always signal the presence of an extreme values. The surface, that is the graph of the function, might be shaped like a saddle right above AB and cross its tangent plane there. So just one thing we can conclude from this paragraph, that a function of two variables can assume extreme values only at domain boundary points or at interior domain points. These lines, we can just extract these lines, and then the second line is that the vanishing of derivatives at an interior point does not always signal the presence of an extreme value. So these two lines are just important for the sake of MCQs if online exam will be take place. So then we can just say that derivative test for local extreme values. So how we can apply the derivative test to find that extreme values are exist there or not. So to find the local extreme values of a function of a single variable, we look for points where the graph has a horizontal tangent line. At such points, we then look for local maxima, local minima, and points of inflection. For a function f of x, y of two variables, we look for points where the surface z is equal to f of x, y has a horizontal tangent plane. At such points, for a function of two variables, we look for points where the surface has a horizontal tangent plane. At such points, we then look for local maxima, local minima, and saddle points. More about saddle points in a moment. Okay, what he said, to find the local extreme values of a function of a single variable, we look for points where the graph has a horizontal tangent line. At such points, we then look for local maxima, local minima, and points of inflection. For a function f of xy of two variables, we look for points where the surface has a horizontal tangent plane. So here is the difference of a function of one variable and two variable. So in a function of one variable, okay, we just observe the graph where the graph has a horizontal tangent line. But in function of two variables, we observe the surface, okay, where the surface has a horizontal tangent plane. So that is the difference between the function of single variable, okay, and the function of two variable. So these two lines are important as the extremum. So here is the proper definition mathematically. So local maxima and local minima. Let f of xy be defined on a region R containing the point AB. Then f of AB is a local maximum value of f if function at the point AB greater than or equal to function xy for all domain points xy in an open disk centered at AB. And f of AB is a local minimum value of f if f of AB less than or equal to f of xy for all domain points xy in an open disk centered at AB. So the concept is similar as compared to the limit of the function. So f of AB is actually a point in the range, and AB is a point in the domain. Okay. So f of AB is a local maximum. It means this is actually a point in the range of f if f the function values greater than equal to f of xy, or you can say all values of the function is less than equal to that fixed value at a b for all domain. So domain points in an open disk center. So the graph of this function will be like a disk. Similarly, f of AB is a local minimum value of f. If f of AB less than or equal to f of xy, it means all the values of the function should be greater than or equal to that value of the function at that point AB for all domain points xy in an open disk centered at AB. So local maxima correspond to mountain peaks on the surface, and local minima correspond to valley bottoms. So it means the local maxima is actually the highest value of the graph, and we just find that what is the peak height of that graph at that point. And local minima is the lowest value, or you can say it's a valley bottom. At such points, the tangent planes, where when they exist, are horizontal. Local extrema are also called relative extrema. As with functions of a single variable, the key to identifying the local extrema is a first derivative test. So we can apply the first derivative test to identify that whether the function has local extremum values at that point or not. Here you can see in the graph local maxima no greater value of f nearby, and local minimum no smaller value of f nearby. A local maximum is a mountain peak and a local minimum is a valley low. So here a first derivative test for local extreme values. If f of xy has a local maximum or minimum value at an interior point AB of its domain, and if the first partial derivative exists there, then f of x partial f over partial x AB is equal to 0, partial f over partial y AB equal to 0. It means that if a function of two variable has a local maximum or minimum value at an interior point AB of its domain, and if the first partial derivative exists, then partial f over partial x at AB should be equal to 0, and partial f over partial y at AB should be equal to 0. So here we don't need to do the proof, so you can skip this proof. So what is the critical point? So critical point, an interior point of the domain of a function. It means critical point lies inside the domain of the function of two variable x, y, where both partial f over partial x and partial f over partial y are 0, or where one or both of partial f over partial x and partial f over partial y don't exist is a critical point of f. So what is the critical point? An interior point of the domain of a function where both partial f over partial x and partial f over partial y are 0, or where one or both of partial f partial x, partial f partial y don't exist is a critical point. So they must have to fill one of the two conditions. So a point is a critical if partial f partial x and partial f or partial y are 0 or any one of them does not exist. So this is the just explanation. So you can read it or it depends on you. Theorem 10 says that the only points where a function can assume extreme values are critical points and boundary points. As with differentiable functions of a single variable, not every critical point gives rise to a local extremum. A differentiable function of a single variable might have a point of inflection. A differentiable function of two variables might have a saddle point. So that is the difference, that a differentiable function, this one, of a single variable might have a point of inflection, and a differentiable function of two variable might have a saddle point. So what is the saddle point? A differentiable function f of xy has a saddle point at a critical point AB if in every open disk centered at AB there are domain points xy where f of xy greater than f of AB and domain points xy where f of xy less than f of AB, the corresponding point AB, f of AB on the surface z is equal to f of xy is called the saddle point of the surface. So here is the saddle point. So what is the saddle point? So for the saddle point, the function should be differentiable. So a differentiable function has a saddle point at a critical point AB if in every open disk centered at AB. So this graph will be like a disk. It means a circular graph. There are domain points xy where f of AB less than f of xy and domain points xy where f of AB greater than f of xy. The corresponding point AB f of AB on the surface is called a saddle point. So example is there, finding local extreme values. Find the local extreme values of f of xy is equal to x square y square. The domain of f is the entire plane and the partial derivative is equal to 2x partial f over partial x. We can just calculate the partial derivative. So partial f over partial x is equal to 2x and partial f over partial y is equal to 2y. Therefore, local extreme values can occur only where partial f or partial x should be equal to 0. So it will imply that x equal to 0, and if 2y equal to 0, it will imply at y equal to 0. Identifying a saddle point, so how we can identify. Find the local extreme values if any of f of xy is equal to y square minus x square. The domain of f is this entire plane so that there are no boundary points and the partial derivative is equal to minus 2x and 2y. So exist everywhere. Therefore, local extrema can occur only at the origin. So to verify that whether local extrema exist, we must to uh, partial f over partial x should be equal to 0. So it will imply that minus 2x equal to 0 and x is equal to 0. So it's a very simple test. You have to calculate the partial f over partial x and partial f over partial y, and we will be uh, able to find the solution that whether the extrema exist or not. So here is another second derivative test for local extreme values. Suppose that f of xy and its first and second partial derivative are continuous throughout a disk centered at AB, and then partial f over partial x AB is equal to partial f over partial y AB equal to 0. Then f has a local maximum at AB if second order partial derivative with respect to x less than 0, and the product of second order partial derivative with respect to x and second order partial derivative with respect to y minus partial derivative of y with respect to partial derivative x greater than equal to 0. It means if the partial derivative satisfy this equation, this inequality, this one, okay, at AB. Number two, f has a local minimum at AB if the partial derivative satisfy this equation at AB. So just the difference between these two conditions is that this is second order partial derivative here is less than 0 in the first condition, and in the second it is greater than 0, and these equations are the same. So no difference in these inequalities, but is the difference here. So f of partial f over partial x second order derivative should be less than 0 in case of local maximum, and second order partial derivative with respect to x should be greater than 0 in case of local minimum. F has a saddle point at AB if this inequality is satisfied at AB. Okay. So you have to remember this inequality, otherwise there is no option to say. And the fourth is the test is inconclusive at AB if this inequality doesn't hold, but it is equality. So is the same, left hand side is the same, but the right hand side also the same, but the sign is equal. So at AB, in this case, we must find some other way to determine the behavior of F. So we just have to remember such kind of definitions, and we don't need to go very deep inside. Okay, note that this inequality can be written in the form of a determinant of a matrix. So, and this is called the discriminant or Hessian of f. It is sometimes easier to remember it in determinant form. So fxx, fyy, fxy, and fxy. This will just, if we open the determinant or calculate the determinant, we will find this equality, you see. So that is also an easy task, not very difficult. So finding the local extremum values, how we can find the local extremum values? Here is an example of it. The function of two variable is there, xy minus x square minus y square minus 2x minus 2y plus 4. Function is defined and differentiable for all x and y, and its domain has no boundary points. The function therefore has extreme values only at the points where partial f over partial x and partial f over partial y are simultaneously 0. This leads to that partial f over partial x must be equal to 0. So then we will find an equation like y minus 2x minus 2 equal to 0. And if partial f or partial y equal to 0, we have an equation of the form x minus 2y equal to 0. Then we solve these equations simultaneously, and we will get x is equal to y is equal to minus 2. So similarly, we will calculate the second order derivative, partial f over partial x and partial f over partial x. So here partial f2 over partial y2 is equal to minus 2, and partial f over partial x into partial f over partial y is equal to 1. The discriminant of f at AB is equal to minus 2. So that's the discriminant we can find in the form of determinant. So then we calculate this equation, and it will result as a 3. The combination fxx less than 0 and the inequality we can calculate here tells us that f has a local maximum at this point. The value of f at this point is f of minus 2 is equal to 8. And now searching the local extremum values, how we can search this one? Find the local extreme values of f of xy is equal to xy. Since f is differentiable everywhere, it can assume extreme values only where. So again we apply the first derivative test, partial f or partial x, and the second order derivative, partial f or partial x equal to z. And this is the Hessian or the discriminant. And next is the absolute maxima and minima on closed bounded region. So we can define as we organize the search for the absolute extrema of a continuous function f of xy on a closed and boundary region are into three steps. List the interior points of R where f may have local maxima and minima and evaluate f at the points. So second is that list the boundary points of R where f has a local maxima and minima and evaluate f at these points. We show how to do this shortly. This even you can skip, so it's look not so important, so you can skip if you want. Okay, so example is that, but you know how to find this absolute extrema. Find the absolute maxima and minima values. F of xy is equal to 2 plus 2x plus. This is the function. So again, you need to compute partial f over partial x and compare it with the 0. You will find the values of f11 is equal to 4. And how we can compute the boundary points? We take the triangle one side at a time on the segment OA y equal to 0 the function. This may be not complicated, but if you will study in the deep, it's look not difficult to you. So on the segment OBX is equal to 0. So this is the geometrical interpretation. Maybe you need to define a triangle like this one, and then it will be easy to calculate the things. And if you will not be able to understand, we will discuss it again in the next lecture again. So this next example is solving a volume problem with the constraints. So that looks a little bit difficult. We can skip this. Summary of max min test. Okay, this we can just revise this one. The extreme values of f of xy can occur only at boundary points of the domain of f. Number two, critical points where partial f of x and partial f of y both equal to 0 are points where partial f of x or partial f of y fail to exist. So this is easy to remember. And the second derivative test is that if the second order partial derivative of x less than 0 and to satisfy this inequality, we can say that local maxima exists on A and B. Similarly, if the second order partial derivative is greater than 0 and it satisfies the inequality, we can say the local minima exists at AB. And similarly, if this inequality is satisfied at AB, we can say that there are some saddle points at AB. And if this inequality does not hold, but an equality holds, then we can say the test is inconclusive and cannot be applied to find the maxima or minimum points. So that is all what we want to say. I can just summarize what we have studied this, that we have discussed the extrema and maxima values. So extremum values where the function has the maximum values and where the function has the minimum values. The maximum values, it's like a peak of the mountain, and the minimum values like the bottom of the valley. And how we can determine rapidly? Just by applying the partial order derivative test. So partial first order partial derivative will just give that whether there exists or not. And similarly, the second order partial derivative test leads to provide us the extrema and minimum values. And then at the end, we will do some of the questions from the this exercise. So these are not very difficult questions. You can do this up to 30. First 30 questions are enough for you. So we can also discuss in maybe the your own language.